Okay, in the last couple of videos, we've been talking about alternating series and how it converges and alternating series remainder theorem. But occasionally, a series may have both positive and negative terms, but not be an alternating series. For example, trig will sometimes do this. So the summation of n equals 1 to infinity of sine of n over n squared is an alternating series, which has some positive terms and some negative terms. When you evaluate sine of 1, sine of 2, sine of 3, sine of etc., those in radians. So this has both positive and negative terms once evaluated, but it is not an alternating series. And sometimes the good hint for you that's not alternating series is that it doesn't have that negative 1 raised to an n or n plus 1 power. Now, the summation of n equals 1 to infinity of the absolute value of s of n over n squared. So if I took the absolute value, so that gets rid of our negative and positive, we can do by direct comparison, if I compare this series with the absolute value of sine of n, and we know that sine of n, because of the graph of the sine function, it falls between negative 1 and 1, so the absolute value of sine of n must be less than or equal to 1 for all n. So we could say that the absolute value of sine of n over n squared is less than or equal to 1 over n squared, because the sine just goes to 1, or less than or equal to the 1. So we're replacing that sine squared with 1. And so thus by direct comparison, we can compare this series with that 1 over n squared series. And we know that's a p series where n is equal to 2. And when a p series where n is greater than 1 converges. So by the direct comparison, the series, the absolute value of n squared over n of sine of n over n squared converges. But does the original series converge? We found the absolute value series converge, but not the original. And so that's kind of what we're going to look at when we look at this absolute convergence theorem. So if a series, the summation, the absolute value a sub n converges, then this series a sub n also converges. So our answer to the question above, yes, it converges. Definition of absolute and conditional convergence. So the summation of a sub n is absolutely convergent if the absolute value of a sub n converges. The series, the summation of a sub n is conditionally convergent if the summation of a sub n converges, but the summation of the absolute value of a sub n diverges. Okay, so let's determine if the following series converges conditionally, absolutely, or diverges. So we have an alternating series here. It appears to be an alternating series, but if I plug in the terms, I will see that this is not alternating series because it's not n negative 1 to the n or n plus 1 or n minus 1. You have that n times n plus 1 divided by 2. That messes it up. So this is not an alternating series. However, when we look at this, it does have some positive terms and some negative terms. So let's expand this series out a little bit so you can see what I'm talking about. We'll do it first, 4 terms. So the first term is negative 1/3. Second term is negative 1/9. Next term is plus 1 over 27 plus 1 over 81 minus etc. So if I look at those, just disregard that negative and positive. So I'm looking at 1/3, 1/9, 1 over 27, 1 over 81. And so when I'm doing the absolute value of this series, I'm disregarding the positive and negative signs. It looks like the series, the summation of n equals 1 to infinity of 1 over 3 to the n, because I have 1 over 3 squared is 9, 3 cubed is 27, 3 to the 4th is 81. So this is actually kind of what the series we're looking at. Now notice this is a geometric series because I can factor out a 1/3, and that leaves me 1/3 to the n minus 1 power. So this is a geometric series where r is equal to 1/3, and because r is less than 1, we know this series converges. And so the absolute value of this series converges. And if the absolute value of the series converges, we know the original series also converges. So our conclusion is this series converges absolutely, or it's an absolutely convergent series. All right, problem B here, this is an alternating series. We have the summation of n equals 1 to infinity of negative 1 to the n divided by the natural log of n plus 1. Okay, so let's compare our a sub n, our a sub n plus 1 term. So a sub n term, if I disregard that positive and negative, so just do our a sub n where we factor out that negative 1 to the n power term. So that a sub n is going to be 1 over the natural log of n plus 1. And we need to compare this with our a sub n plus 1 term, which would be 1 over the natural log of n plus 1, which is n plus 2. And so that's going to make our a sub n plus 1 be smaller than our a sub n term. So it is decreasing. And then now let's see our limit as n goes to infinity of 1 over the natural log of n plus 1. Well, that's just 0. And so it meets the 2 requirements of the alternating series test. So I know the original series converges by the alternating series test. Our next step is to check and see if it is conditionally convergent or absolutely convergent. So that means I need to see what's happening to the absolute value of a sub n, which is just simply 1 over the natural log of n plus 1. And so let's do direct comparison. So we'll do direct comparison. We'll compare this to harmonic series, 1 over n. And remember, we know the harmonic series is a divergent series. So we need to figure out 1 over n or 1 over the natural log of n plus 1, which is smaller. And so looking at some terms or looking at what's happening algebraically, we know what's going on. I can see that since 1 over n is less than 1 over n plus 1, our divergent series is smaller than our given series. And so we can say that this series diverges by the direct comparison test. So the absolute value series diverges by the direct comparison test when we're comparing the absolute value of a sub n to 1 over n. And so since I got convergent to original series, divergent for the absolute value, our conclusion is this series is, the series given is conditionally convergent. Okay, part C here, we got the summation of n equals 0 to infinity of negative 1 to the n over n factorial divided by 2 to the n. Okay, so this is an alternating series, and so my a sub n term, therefore, is going to be n factorial over 2 to the n. And the limit as n goes to infinity of n factorial over 2 to the n. Well, n factorial gets larger faster than 2 to the n, so this goes to infinity. And so the alternating series test fails in this case. So we got to figure out another way to determine if this series converges or diverges. So let's try nth term test. So let's figure out the limit as n goes to infinity of negative 1 to the n times n factorial over 2 to the n. And so let's see, on the top, we got factorials. So that's going to go to infinity. And the bottom, faster than the bottom. So this is going to be plus or minus infinity. And since we had a limit does not equal 0, we know that this series diverges by the nth term test. And so I don't have to test for conditionally or absolutely divergent. And then we stop. Okay, looking at our last example, D here, where the summation of n equals 1 to infinity of negative 1 to the n over n, the square root of n. So this is an alternating series. Our a sub n term is 1 over the square root of n. The limit as n goes to infinity of 1 over the square root of n. Well, that's the same. That's equal to 0. And so let's compare our a sub n, our a sub n plus 1 term. And we see that our a sub n plus 1 term is less than our a sub n term. And so we can say this converges by the alternating series test. So we have a convergent series. So let's determine if we have a absolutely convergent or conditionally convergent series. And so we need to find the summation of n equals 1 to infinity of the absolute value of negative 1 to the n over the square root of n. Well, that just simplifies down to the summation of n equals 1 to infinity of 1 over the square root of n. And 1 over the square root of n is same as 1 over n to the 1/2 power, which makes this a p series, where p is equal to 1/2. And so if 1/2 is less than 1, so we know that this is a divergent p series. So the absolute value sequence diverges, but the original series converges. So our conclusion is the series is conditionally convergent.